Okay, integration by parts. Now, every differentiation rule that we looked at before has a corresponding integration rule. The substitution rule that we looked at corresponds to the idea of the chain rule. Integration by parts, which is what we're about to talk about right now, it actually corresponds to or has a connection with the idea of the product rule. It actually starts, the whole process starts with the idea of the product rule. Now, integration by parts works actually very, very well for a combination products of algebraic and transcendental functions. And like I said, the basic idea actually starts with the idea of the product rule. So, review quickly the product rule. d dx of f of x times g of x is f of x times g prime of x plus f prime of x times g of x. So that's just your basic product rule for differentiation. Now, if I integrate both sides, on the left-hand side, I will simply have f of x times g of x is equal to the integral of f of x times g prime of x dx. I'm going to split this up into two integrals right away, plus the integral of f prime of x g of x dx. Now, what I'm going to do is I'm going to solve this for f of x g prime of x. And when I do, what I get is the integral of f of x times g prime of x dx is equal to f of x times g of x minus the integral of g of x f prime of x dx. That's this piece right here, and I simply change the order slightly. So what good does that do us? Well, what I want to do is I want to relabel some of these. I'm going to call u, let's just say I'm going to let u equal f of x in this case. That then implies obviously that du equals f prime of x dx. And I'm going to let dv, or actually v, equal g of x. That would imply that dv is equal to g prime of x dx. Now, using that notation, what I actually have is the integral of f of x, which is u, times g prime of x d of x, well that's dv, is equal to f of x, which is u, times g of x, which is v, minus the integral of g of x, which is v, times f prime of x dx, which is du. So what this actually did is this right here is what we think of as the rule that we refer to as integration by parts. So if I look at an integral and I can think of it in the terms of u times dv, then by using these pieces, these parts, I can actually go ahead and complete the integration. So that may make this a little bit more sense when we jump to an example here. So hold this idea. The choices of u and dv are extremely critical. Remember, I need my original function I'm trying to integrate to have the form of u times dv, the integral of u times dv. So picking what part you're going to call u and what part you're going to call dv is extremely critical. As a hint, you may try letting dv be the most complicated portion of the integrand that fits a basic integration rule. So we need to integrate part of this. So I want to have something, the most complicated piece in there, that I know how to easily integrate. And then just simply let u equal everything else. Another strategy would be to let u be the portion of the integrand whose derivative is a simpler function than u. So I have a function that I'm going to call u, and the derivative of that is at a simpler function. And then let dv be everything else. This is basically two different strategies you can try while trying to work out an integration by parts. So let's take a look at this first example. I need to integrate x times e to the x. Now, right now, we don't know how to integrate this. We don't have a tool to actually complete this integration. But I'm going to let u equal x. That would then imply that du equals the derivative of x dx, which is just 1 dx, or simply dx. That would mean that dv must be e to the x, which means that v equals the integral of e to the x dx, which is simply e to the x. Now I have all the pieces I need to put this together. Therefore, the integral of x e to the x dx is actually equal to, I'm going to write this down for you, how about right here? Just as a reminder, the integral of u dv equals uv minus the integral of v du. That's the format that we're trying to follow. So I need u times v, that's x, v is e to the x, so x times e to the x, minus the integral of v, which is e to the x, du, and du is simply dx. So that's going to be x times e to the x minus, what's the integral of e to the x? E to the x. E to the x. So I could rewrite this as simply, if I wanted to, e to the x times x minus 1. And of course, we can't forget, because this is an indefinite integral, we need that constant of integration. Don't forget to add that constant of integration there, c. So that's the solution. If you integrate this, if you differentiate this, you will end up with the original integrand. All right, let's take a look at another example. How about x squared times e to the negative x dx? Well, I'm going to start off with basically the same idea. I'm going to let u equal x squared. That means that du equals 2x dx. Everything else is then e to the negative x. So I'm going to say dv equals e to the negative x, which means that v equals the integral of e to the negative x dx, which equals a negative e to the negative x. So now once again, I have my components. Therefore, based on integration by parts, the integral of x squared e to the negative x dx will be equal to uv, which is x squared. I'm going to bring that down because I just realized I didn't leave myself too much room there. So I'm going to come down and work. uv, which is x squared times negative e to the negative x. So I'm just going to put my negative out there, e to the negative x, minus the integral of negative e to the negative x times 2x dx. So now I'm going to just rearrange this just a little bit, and this is actually equal to negative x squared e to the negative x. The double negative here becomes a positive, plus, I'm going to pull this constant out, 2 times the integral x e to the negative x dx. So now if I can integrate this last piece, put it back together, and I'm done. I don't know how to integrate that as it sits, so use integration by parts. I can use integration by parts repeatedly as needed to ultimately get down to this end function. So just looking at this, just this piece right here, I'm going to use integration by parts again. I'm going to let u equal x. That means du is dx, which leaves me as dv as being e to the negative x, which means v equals the integral of e to the negative x dx, which is just a negative e to the negative x. So I have the pieces. And that would then give me that the integral of x e to the negative x dx is actually equal to uv. That's negative x e to the negative x minus the integral of v du. Well, I'm going to have a double negative, so it's going to be a positive e to the x dx, which is just a negative x e to the negative x. Oops, I missed my negative there. Minus e to the x. So now I need to put this all back together. I'm going to bring this straight down. And I'm going to say, therefore, my original integral of x squared e to the negative x dx is actually equal to, can't forget my 2, I'm going to have a negative x squared e to the negative x, negative x, plus 2 times this integral, which is a negative x e to the negative x minus e to the, this should be a negative x, I see there, negative x, sorry about that. And there it is. I mean, clearly there's quite a bit I can do in terms of simplification, which you should definitely do, but I'm not going to waste time with that now. It's just algebraic simplification. Add my constant of integration, do some algebraic simplification, and that one's done. So let's take a look at another example. How about e to the x sine x? Now here, I'm going to let u equal e to the x. That means that du equals e to the x dx. And then that would then imply that dv is sine x, which implies that v, if I integrate sine x, I'll get negative cosine of x. So let's put the pieces together. Therefore, the integral of e to the x sine x dx actually equals uv, which is a negative e to the x cosine of x, minus, let me come down here a bit, minus the integral of v, which is negative cosine of x, du, which is e to the x dx. So what I want to end up with, I'm going to write this one more time, negative e to the x cosine of x, I have a double negative, so plus the integral e to the x cosine x dx. Again, to finish this up, I'm going to need to use integration by parts again. So for just this piece, I'm going to once again let u equal e to the x, then du equals e to the x dx. That means that dv will be cosine of x, which implies that v, the integral of cosine is sine, is simply sine x. So this piece will actually be equal to uv, that's e to the x sine x, minus the integral of v, which is sine x, du, which is e to the x dx. So let's put all this together now. What this is telling me is that the integral of e to the x sine x dx is equal to, I have this first piece right here, a negative e to the x cosine of x plus this integral, which is actually right here, that's e to the x sine x minus the integral of e to the x sine x dx. Now, that may feel like we're running around in circles, and that's only because we are. This is our original problem, right there. However, notice that this is a negative and this is a positive. In other words, they won't cancel each other out, and that's a good thing. So what I'm going to do is I'm going to move the integral of e to the x sine x dx on the right over to the left. And when I do that, this will give me 2 times the integral of e to the x sine x dx equals, if I factor out the e to the x here on this one, I'll have e to the x times sine x minus cosine of x. If I divide by 2, that gives me the integral of e to the x sine x dx, oops, I kind of forgot an x there, didn't I, is equal to e to the x sine x minus cosine x divided by 2, and now I'm going to add that constant of integration. So that's it. That's the basic idea and a couple of examples behind integration by parts.